Imagine this. A massive new app launches. Everyone's hyped about it. It's got this sleek interface, incredible features. I mean, the design even won awards before it went live. But then, day one, it freezes. Or maybe worse, it silently starts corrupting user data. Or think about this. A company sinks millions, literally millions of dollars, into a gleaming new enterprise system. And the employees, they actively boycott it. They just flat out refuse to use it. So what went wrong there? Was the code just bad? Was the design flawed right from the start? Or maybe did they completely miss the most crucial steps, the ones that happen after the big launch, the ones that really make or break a system?
Yeah, those aren't just scary stories, are they? That happens. The digital world, I mean, our whole connected economy, it doesn't run on magic. It definitely doesn't. It runs on systems that are meticulously designed, yes, absolutely. But critically, it runs on systems that are successfully implemented and then maintained. And understanding how to navigate those really complex final stages of the system development life cycle, making sure your brilliant designs actually come to life and then stay alive, well, that journey starts right here, right now.
Welcome back to the deep dive. This is where we unpack complex topics to make you genuinely well-informed and hopefully a bit faster. Today, we're peeling back the layers on system implementation and maintenance. These are kind of the unsung heroes of the SDLC, the system development lifecycle. And for you, the aspiring MIS, CIS, IT, or really any business student, especially those in BCIS 3389 at the Dr. Sam Pack College of Business, this isn't just about textbook theory from modern systems analysis and design. This is about gaining skills that are really in demand, the kind of skills that will position you for impactful careers, shaping the digital systems that, well, power pretty much everything. It's about making sure your designs don't just stay on paper, but actually thrive out there in the real world. Okay, before we get too deep into the weeds here, if you're finding value in these insights, please just take a quick second, hit that like button, subscribe to our channel, maybe share this deep dive with a friend who might need it. You really won't want to miss our insider tips that could seriously help position you for a bright future in whatever career path you choose. And as always, don't forget to check the description down below. We've put together some additional resources there that we think you'll find incredibly valuable.
All right, let's kick things off. Let's talk about where all that hard work, all that analysis and design you've been meticulously crafting, maybe in BCIS 3389, finally starts to pay off. Implementation. This is really where the rubber meets the road. It's the process, the actual doing of taking those abstract plans, those detailed designs, those standards you've worked out, and transforming them into a living, breathing, operational system. We're really talking about guiding a client or your own organization from the moment they acquire software or hardware to its actual practical use, getting it working day to day.
Okay, so it's definitely not just about the coding then, because I think a lot of people, when they hear system implementation, their mind immediately jumps to developers, right? Hunched over keyboards, churning out lines and lines of code. But you're saying that's just one piece, maybe even a smaller piece than we think, of a much larger, more intricate puzzle.
Exactly. That's a really common misconception, and it's a huge one. While coding is absolutely a core component, I mean, you have to translate your design specs into executable programs. Implementation covers so much more ground. Think of it like preparing for opening night for a major Broadway play after months and months of rehearsals. You've got the script, the set design, the costume sketches. That's your analysis and design phase. But implementation, that's the entire production. It's the actors learning lines, the lights getting rigged just right, the sound cues being perfected, the stage managers coordinating everything. In our world, this phase involves rigorous testing, and I mean rigorous. It's absolutely non-negotiable. We'll get more into that later. Then there's the strategic installation, getting the system onto the right hardware, configured correctly, accessible to the users. After that, comprehensive documentation, all those user manuals, system guides, technical specs. People need to know how it works, how to fix it, and crucially, essential user training, preparing your entire workforce or customer base for these new tools. You can't just drop it on them. And finally, robust support. Because the system's journey doesn't end on launch day. Honestly, it's just beginning. Your ability to apply those basic systems concepts, that KO3 outcome, means understanding how all these different elements have to work together seamlessly to bridge that gap between the abstract design and the concrete impact.
That analogy of opening night is perfect. It really highlights that technical perfection, the code being flawless, isn't enough. The audience, or in our case, the users, they have to embrace it. They have to use it effectively. And you mentioned strategic installation. That brings us to a really critical decision point, doesn't it? Once your system is built and, thoroughly tested, how do you actually introduce it? How do you get it into the hands of users and integrate it into their daily operations? It's definitely not just flipping a switch. From your experience, what are the main deployment options companies usually wrestle with? And maybe what are some of the hidden traps in each of those?
That's a fantastic question, and it really gets right to the heart of project management methodologies, doesn't it? That KO5 outcome. Many students, they learn about the four main deployment strategies, but the real challenge, the thing you grapple with in the real world, is choosing the right one for a specific context. You have to weigh the trade-offs constantly. Okay, let's start with direct cutover. This one's the most straightforward, I guess. You basically shut down the old system and bam, you instantly switch on the new one. It's like ripping off a Band-Aid, quick, decisive, and often it's the least expensive, at least in the short term, because you're not paying to run two systems at the same time. But the hidden trap here, the risk, it's absolutely monumental. If that new system fails, even for a few hours, your operations just halt completely. There's zero safety net. I've seen small businesses use this maybe for a simple, non-critical internal tracking tool where a day or two of downtime isn't the end of the world. But for anything central to a business, it's a huge gamble. I remember this one small e-commerce startup. They decided to do a direct cutover for their entire order processing system. Just switched it overnight.
Oh, no.
And the next morning, they couldn't process a single order for like half the day. Chaos. Luckily, they were small enough they managed to recover, but the hit to their reputation, their immediate revenue, it was brutal. Real lesson learned.
Ouch, yes. So high risk, maybe high reward if it works perfectly, but mostly just high risk.
Got it. What's the opposite end of that spectrum then?
Yeah.
The super cautious approach. The complete opposite would be parallel operation. Here, you run both the old system and the new system simultaneously for a defined period. You keep the old system humming along as a complete backup, while the new one is thoroughly proven in the live environment. The big pro here is safety. It's unparalleled, the lowest risk approach by far. Think about a bank upgrading its core transaction processing system. I mean, for them, even an hour of downtime is absolutely unthinkable, right? So they need total assurance the new system works flawlessly before they even think about retiring the old one. However, the downside is cost and complexity. It's easily the most expensive option because you have redundant operational costs running two systems, potentially needing more staff to manage both or enter data twice. Plus, it can be incredibly confusing for users. Imagine having to enter the same sales order into two different systems. The chance for errors just skyrockets. It's kind of like training for a marathon by, running two marathons at the same time. Exhausting and complicated.
Yeah, cost and complexity sound like major deterrents. But I can see how for those really mission-critical systems, that safety net is probably worth every single penny. Okay, what about something in between? A more gradual approach, maybe.
That brings us nicely to phased implementation. With this strategy, you bring the new system online gradually. Often it's done module by module or function by function. So instead of one massive switch, it's a series of smaller, more controlled rollouts. The benefit: definitely reduced risk compared to a direct cutover since you're not putting the entire operation on the line all at once. It also allows for really valuable learning and adjustments along the way. You can fix kinks in one phase before moving to the next. Plus, it spreads out the workload, which can be easier on the implementation team and the users. A common example is rolling out a new ERP system that's enterprise resource planning. Maybe you start with the inventory management module, get that working smoothly, then add sales orders, then maybe the finance modules later on, or you roll it out department by department. The main pitfall here, though, is the longer overall implementation time. It just takes longer to get the whole system live. And managing the interdependencies between the old and new modules or the phased-in modules can get really complex.
You have to be meticulous about ensuring different parts of the system still talk to each other correctly during that staggered rollout. It requires careful planning.
That makes a lot of sense. It sounds like a more manageable way to kind of dip your toes in rather than jumping head first. Okay, what's the fourth option? The one that tests the waters in a really specific way.
Right, that would be pilot implementation. Sometimes people call it single location deployment. Here, the new system is fully deployed, but only at one specific site, or maybe with just a small, selected subset of users. If it proves successful there, then it's rolled out to the rest of the organization. This allows for really thorough testing in a genuine real-world environment, but with limited impact. Any problems that crop up are contained within that small pilot group. It provides an incredibly valuable feedback loop before you commit to a wider rollout. A great example is, say, a retail chain implementing a brand new point-of-sale system. They might deploy it in just one or two stores first, work out all the bugs, refine the training, then deploy it company-wide. The drawbacks: well, it can be slow, especially for really large organizations. Rolling out site by site takes time, and choosing the right pilot site is absolutely critical. You need it to be representative. The hidden trap here is what we call selection bias. Sometimes teams pick the easiest department or the most tech-savvy location for the pilot. It looks great. But then the system fails when it hits a more demanding or less prepared part of the organization. So choosing that pilot group carefully is key.
Okay, so as IS professionals or future IS professionals, applying those project management methodologies we learned about, KO5, our role isn't just knowing these 4 options exist, it's about deeply understanding the context, right? The project scope, its complexity, the budget constraints, the organization's tolerance for risk. All of that goes into recommending the absolute best fit. No wonder companies often stumble at this stage. It really is a strategic tightrope walk.
And that strategic tightrope walk, it leads us directly into the absolutely critical importance of testing. Host, something that always just astonishes me, even after doing this for years, is the sheer economic reality behind system quality. Let's talk about the actual cost of bugs, which relates directly to applying those basic economic models. KO1. It's a staggering truth, really. Fixing a bug discovered during the implementation phase. It can be roughly 6 times more expensive than addressing that same bug if you'd found it earlier, back during the design phase.
6 times. Wow, that's a huge jump already. And it gets worse, right? I mean, if that bug actually makes it out to the customers.
Oh, it absolutely gets worse, much worse. If an error slips through and is only detected after the product has been released to users, now we're talking maybe 4 to 5 times costlier than fixing it during design, but potentially up to 100 times more expensive than if it were caught way back then or even during maintenance. Think about that ripple effect. It's not just the monetary cost of the developers fixing the code anymore. It's the damage to your brand's reputation. It's the loss of customer trust, which is incredibly hard to win back. It's potential legal liabilities, depending on the bug. It's the impact on your team's morale constantly fighting fires is exhausting, and it can completely derail project timelines and future plans. A bug found too late can fundamentally erode trust, both inside the organization and externally with your customers and partners. This economic reality alone should underscore the immense value of robust, and especially early, testing efforts. Testing isn't a luxury you tack on at the end. It's a strategic imperative for financial performance, for customer satisfaction, for survival, really.
So it's not just about finding bugs. It's really about finding them at the cheapest, least disruptive point in the whole process, which means testing absolutely cannot be an afterthought, something you just squeeze in before launch if you have time. What are some of the key layers of assurance, the different types of testing we put in place to try and catch these issues early?
Precisely. Testing has to be an integral, ongoing part of the entire development cycle, woven into every stage, really. And for testing to be truly effective, it's absolutely crucial to set smart objectives. Specific, measurable, achievable, relevant, and time-bound goals for your testing. You need to know exactly what you're testing for, what specific functionality, what performance metric, how will you measure success, what are the acceptable limits or thresholds. This isn't just about throwing a bunch of random tests at the code and hoping for the best. It requires a clear strategy. It's a foundational project management skill, KO5, that ensures your testing efforts are focused, efficient, and deliver actionable insights, not just noise.
Absolutely. Building that quality in from the very start saves a tremendous amount of pain and expense down the road. And to achieve that quality, we typically use different layers of assurance, right? Different types of testing, each with a really specific focus. We usually start small with unit testing. This involves testing individual program components, sometimes called modules or functions, in complete isolation. The goal is to find errors specifically within their code, separate from everything else. Think of it like a quality check for each individual brick before you start building the wall. A common technique used here is something called stub testing. This is where you use simple placeholder code to substitute for any subordinate modules that the unit you're testing calls, but which aren't built yet or available. It lets you test the logic of one piece without needing the whole system to be complete. Okay, so once those individual units, those bricks, seem solid, we move up a level to integration testing. This is where we start bringing together all the modules that make up a single program or a cohesive feature and test how they interact with each other. It's all about checking the connections between those bricks, right? Ensuring they fit together properly, pass data correctly, and communicate as expected. Modules are typically integrated in a top-down incremental fashion. You add them one by one or in small groups and test the interfaces as you go. Makes sense. Then, after the modules are integrated into programs, we zoom out further for system testing. This is where we bring together all the programs that make up the complete system and test them as a whole. We're verifying the end-to-end functionality now. This is testing the entire wall, not just the individual bricks or how they connect to their immediate neighbors. For example, if you're building an inventory control system, system testing would involve making sure all the parts work together seamlessly, from scanning an item at receiving to updating the stock levels in the database, to generating purchase orders when stock is low, to producing inventory reports for management. It tests the entire business process flow through the system. And then there's the final hurdle, which is arguably the most critical stage of testing from a business perspective: user acceptance testing, or UAT. This is where the actual end users, the people who will be using the system every single day to do their jobs, get their hands on the completed system. They test it using real-world scenarios, their actual business processes. Their goal is to validate that the system meets their requirements, that it's usable, and that it actually helps them do their job effectively. It's essentially their stamp of approval, ensuring the system is truly fit for purpose from their perspective. A best practice here is definitely to develop your UAT test cases based on those real-world business scenarios. You need to provide UAT environments that closely mimic the production setting. And crucially, you need to get formal sign-off from key stakeholders before you go live. This directly ties into your skills outcome, that SO13, of implementing diagrams from business cases. UAT is fundamentally testing whether those business cases, those use cases and activity diagrams you design, have been correctly translated into a working, usable system that delivers the intended value.
And beyond these core types, host, we have a whole range of specialized testing that delves even deeper into various critical aspects of system robustness and quality. First, there's performance testing. This evaluates how well the system actually performs under different kinds of load. And this itself breaks down into several subtypes. There's load testing, which evaluates system behavior under expected normal usage conditions. For example, how does it perform with, say, 100 simultaneous users doing typical tasks? Then there's stress testing. This takes it much further. It assesses the system's absolute limits by applying extreme workloads, pushing it until it actually breaks, maybe simulating 1,000 simultaneous users or bombarding it with transactions. The goal is to understand its breaking point and, just as importantly, how gracefully it recovers. And related to that is scalability testing, which specifically determines the system's ability to handle increased demand gracefully over time. Can it support growth? For all of these, automated tools are pretty much essential. They allow you to simulate various user loads accurately and consistently and monitor key performance indicators, KPIs like response time, throughput, error rates, resource utilization. They give you quantifiable metrics on system behavior under pressure. Then, absolutely critical today, we have security testing. In this era of, constant cybersecurity threats and data breaches, this is an absolute imperative. It's not just a nice-to-have feature. It's fundamental. It's all about safeguarding sensitive data, maintaining that hard-earned customer trust, and avoiding the potentially astronomical costs and reputational damage of a security incident. Common methods include penetration testing, where ethical hackers actively try to breach the system to find vulnerabilities. There's also vulnerability scanning, using automated tools to identify known weaknesses based on signatures, and focus code reviews, where developers specifically look for security flaws in the source code itself. Crucially, all security testing must be conducted in a secure, controlled environment. You don't want your tests accidentally exposing real data. Companies like Global App Testing, for instance, highlight their ISO 27001 security certificate as evidence of the enterprise-grade security needed for reliable testing.
That's such a critical area, especially with how sophisticated cyber threats are becoming. But what about testing for the unexpected? The things users aren't supposed to do, but inevitably will.
Excellent point. That's precisely what negative testing is for. While positive testing confirms that the system works correctly with valid inputs and expected user actions, negative testing deliberately subjects the system to invalid or unexpected inputs. The goal is to reveal potential bugs, errors, or even security vulnerabilities that might go completely unnoticed during normal positive testing. It's absolutely crucial for building robust, resilient systems that don't just crash or behave unpredictably when users do something slightly out of the ordinary, like trying to type letters into a phone number field, or submitting a form with required fields left empty, or clicking buttons in the wrong sequence. It's essentially about trying to break the system in controlled ways to ultimately make it stronger and more foolproof. We also rely heavily on regression testing. This is vital, absolutely vital, for preventing unintended consequences whenever new code changes are introduced or features are added. Its purpose is to verify that the existing functionality, the stuff that was already working, still works correctly after the modifications have been made. Imagine you've just fixed a batch of 50 tricky bugs. You absolutely must run regression tests to ensure those fixes haven't inadvertently broken something else entirely, somewhere else in the system. It happens all the time. Best practice here is definitely to use automated test suites for regression testing, as they can be executed quickly, consistently, and repeatedly. Using version control to track changes is also key. Regression testing should be conducted consistently throughout the development lifecycle every time there's a significant change to maintain confidence that the software remains stable and reliable. And finally, this brings us to a really important modern concept: shift-left continuous testing. This idea is a bit of a game changer in how we approach quality. It emphasizes integrating testing throughout the entire SDLC right from the very beginning, rather than treating it as a separate phase tacked on at the end. It's about early and continuous verification of software quality. Instead of waiting until development is done to start testing, you test smaller pieces much earlier and more frequently. The benefits are significant. You often see reduced development time and costs because bugs are caught when they're cheaper to fix.
You get improved reliability, faster feedback loops leading to quicker defect resolution, and generally enhanced collaboration between developers, testers, and business stakeholders. This approach directly aligns with the BCIS 3389 focus on systematic analysis and design, making quality an integral part of every single step, not an afterthought. It helps ensure a positive user experience and software that works smoothly right from inception.
Those specialized tests are clearly vital for achieving comprehensive quality assurance, and where they happen, the environment is just as important as the tests themselves, isn't it? To effectively isolate the effects of changes and gauge their impact independently, we rely on a set of diverse testing environments, which ideally should replicate the eventual production setting as closely as possible. First up, you've got the development environment. This is basically the developer's playground. It's where the coding happens, the initial debugging, and the very first informal tests are run by the developers themselves. It's their sandbox for building and iterating quickly, often on their local machines. Then we move to a more formal testing environment, sometimes called QA environment. This is purpose-built and specifically configured for the various types of testing we just discussed: unit, integration, performance, security, and often UAT as well. It's a much more controlled space, usually managed by dedicated QA teams, designed for rigorous evaluation away from the developer's immediate workspace. The staging environment comes next, just before the final leap. This is intended to be a scaled-down but otherwise identical replica of the actual production environment. It's used for those final checks, dress rehearsals, and simulating the go-live conditions as closely as possible before the actual deployment. Think of it as the last chance to catch any unexpected integration issues or configuration problems before they impact real users. Then, of course, you have the production environment. This is the real deal, the live environment. It's where the software is actually deployed and used by end users to conduct real business. It's obviously the most critical environment, as any issues or errors here have immediate real-world consequences for the business and its customers. This is where all those previous layers of testing truly prove their worth or reveal their shortcomings. We also need to consider the disaster recovery environment. This isn't for testing per se, but it's a critical parallel environment. It's a separate setup, often geographically distinct, specifically designed for recovering operations in case of a major failure or disaster affecting the primary production environment. It ensures business continuity and is a vital part of risk management. It's your ultimate insurance policy. And last, but certainly not least, especially for learning and experimentation, there's the sandbox environment. This is a flexible, isolated space. It's primarily used for things like experimentation, trying out new features, user training, or testing configuration changes without any risk of affecting the live production system or its precious data. For you as a student, this is invaluable. This is where you can safely practice implementing those UML diagrams, KO4, SO13, experiment with different system configurations, maybe try breaking things intentionally to see what happens, and troubleshoot issues without any real-world consequences. It's an essential learning ground for applying those basic systems concepts, KO3, in a practical, hands-on, risk-free way.
Okay, so you've built it, you've tested it rigorously. Now comes the part where it gets really interesting, host. And often, this is where things get quite challenging, honestly. When we introduce these powerful new systems, we frequently run head-on into what is often the single biggest hurdle of all: resistance to change. That's KO2 right there. Digital transformation efforts, it doesn't matter how technically brilliant the system is or how efficiently the code runs, they fundamentally hinge on your workforce's collective acceptance and their adaptability. Research from folks like Deloitte, for example, consistently highlights resistance to change as the #1 hurdle in technology adoption. It often beats out technical issues or budget constraints.
So it really boils down to the people, doesn't it? It's not just about the silicon and the software, but the psychology of the individuals who actually have to use this new thing day in and day out. Why do people resist something that's supposedly better? What's that hidden psychological hurdle that makes us want to cling to the old ways, even if we know they're inefficient or outdated?
It's fascinating, and it's deeply rooted in human nature, isn't it? We tend to resist change for a number of reasons. Often it's simply comfort with existing processes. We know how to do it the old way. It's familiar. It feels safe. There's also often a genuine fear of the unknown. People worry, what if I can't learn this new system? What if it makes my job obsolete? What if I look stupid trying to figure it out?
Hmm.
Sometimes it's just plain skepticism about the promised benefits. They've heard promises before, maybe have been burned by failed implementations in the past. And sometimes, honestly, it's just inertia. Like Newton's first law applied to organizations. An object at rest tends to stay at rest. Employees get accustomed to certain routines, certain ways of working, and anything that disrupts that comfortable equilibrium, even if it's ultimately for the better, can trigger apprehension, anxiety, sometimes even anger or resentment. I remember rolling out a new email system once, supposedly much better. For weeks, half the team was still printing out important emails and discussing them physically at the water cooler. It wasn't about the tech being bad. It was about breaking that ingrained routine of the morning printout and chat. It was a habit. And the organizational impact of this resistance, if it's not managed well, is profound. Modern organizational change is often driven by external technological innovations, new software platforms, AI tools, whatever it is, and these forces compel rapid adaptation. Companies that can manage that change effectively, that can adapt quickly, they gain a significant competitive advantage. Those that don't, that get bogged down by internal resistance, they often get left behind. They can face serious losses in profit and market share. And it directly affects employee morale, too. Uncertainty, lack of support, feeling forced into something that leads to disengagement, lower productivity, higher turnover. So managing this human element effectively isn't just a soft skill. It's a core strategic imperative that directly impacts your economic and organizational models. KO1, KO2. It's business critical.
That's such a crucial point, and it really goes way beyond the technical aspects of implementation. It sounds like this human element, this resistance, can truly make or break even the most technically brilliant system. And that's exactly where change management comes into play, right? It's not just about managing the project, it's about managing the change itself. It's a whole discipline focused specifically on preparing, equipping, and supporting individuals, teams, and leaders as they navigate these organizational transitions. It's really about having a structured approach to ensure that changes are implemented smoothly, successfully, and importantly, that the benefits actually stick. What typically drives all this change in the first place? I mean, beyond just, oh, here's the next shiny new technology. Obviously, the constant evolution of technology itself is a huge driver, always pushing organizations towards new systems and platforms, but it's also things like internal process reviews, finding better ways to do things. Shifting customer demands and expectations play a big role. Intense competitive pressure forces companies to adapt. Mergers and acquisitions almost always involve system integration and change. Even organizational restructuring can trigger the need for new systems or processes. For business students like you listening, understanding these underlying drivers is absolutely critical for strategic decision making. They explain the why behind major system implementation projects and how they impact the entire business. Now, the roots of change management as a discipline go back quite a few decades, and they offer some foundational models that we still build upon today. One of the earliest and maybe most fundamental is Kurt Lewin's three-step model. It's actually quite elegantly simple, isn't it? First, unfreezing. This means breaking down the old habits, the existing mindset, the old ways of doing things to make people actually willing to accept that change is necessary, shaking up the status quo. Second, changing. This is the stage where you actually implement the new ideas, introduce the new processes or systems, often through collaboration, training, and direct action. And finally, refreezing. This involves stabilizing the new norms, embedding the new ways of working into the organizational culture so they become the normal, accepted way of life, solidifying the change. While it's elegantly simple, expert, where does this foundational model maybe fall a bit short in today's world? Especially thinking about how rapidly tech evolves now or in environments using agile methods. What complexities does refreezing not fully capture?
That's a really insightful question, host. Lewin's model provides a fantastic mental framework, a great starting point. But you're right, in today's world of constant digital disruption, and particularly with agile development methodologies, that final refreezing step can feel, well, almost impossible sometimes. Systems are rarely static enough anymore to be truly refrozen into a stable state for long. Modern technology often requires continuous adaptation, iteration, ongoing improvement. So the unfreeze, change, refreeze cycle itself often needs to be much faster, more iterative, almost continuous. We often talk about being in a state of perpetual beta, always evolving. Lewin's model, developed in a very different, more stable industrial era, doesn't fully account for that constant churn. Building on Lewin's foundational work, though, we have John Kotter's 8-step process for leading change. This offers a much more detailed step-by-step approach. It's become very influential. It starts with creating a powerful sense of urgency. Why do we have to change now? Then building a guiding coalition, getting the right people with enough power on board. Forming a clear strategic vision and initiatives. Enlisting a volunteer army of employees who are enthusiastic supporters. Enabling action by systematically removing barriers, like old structures or lack of skills. Generating short-term wins to build momentum and show progress. Sustaining acceleration, not letting up too early. And finally, instituting the change deeply into the organizational culture. A great example often cited is how the Centers for Disease Control and Prevention, CDC, used Kotter's model to improve preventive care services within a specific Kentucky health center. They moved systematically from assessing the current state urgency to implementing higher quality standards, enabling action, generating wins, and then evaluating the impact, instituting change. It's much more prescriptive than Lewin's, offering clear actions for leaders to take. Another really powerful framework, especially relevant for training and individual adoption, is the 80-CAR model. This one focuses specifically on the individual's journey through change, rather than just the organizational process. 80-CAR City is an acronym for 5 key building blocks that individuals need to achieve for change to be successful. Awareness of the need for the change. Desire to participate and support the change. Knowledge of what to do during and after the change. How to use the new system, for example. Ability to actually realize or implement the change as required. Having the skills and competence. And finally, reinforcement to ensure the results of the change stick and don't fade away. It's a very prescriptive, goal-oriented framework. It's great because it helps you assess where individuals might be struggling in the change process. Do they lack desire or knowledge or ability? It allows you to tailor interventions like training or communication much more effectively. And then more recently, reflecting the shift towards more agile ways of working, we've seen the emergence of lean change management. This is a modern, highly adaptable approach inspired by concepts from lean startup and agile software development. It focuses less on rigid, predefined, top-down plans and more on creating a shared purpose, fostering meaningful dialogue and co-creation with those affected by the change, running small experiments to see what works, understanding the response to those experiments, and adapting accordingly. It's designed to help change agents create a much more adaptable contextual approach to managing change, especially in rapidly evolving environments where you can't predict everything up front. It embraces feedback and iteration.
Okay, so these models provide really valuable roadmaps for navigating the often messy human side of organizational transitions. But even with the best change management plan in the world, if users don't actually know how to use the new system effectively, it's all pretty much for naught, right? That's where effective end-user training becomes absolutely paramount. It's not just a nice to have, it's essential.
Absolutely essential. End-user training and your ability to communicate effectively in writing about it, W01, is the ultimate bridge between all that technological potential you've built and its actual practical utility in the business. It's absolutely vital for ensuring successful technology adoption, for maximizing the return on that huge investment, ROI, the company just made, and critically, for achieving the specific business outcomes, KO1, the system was intended to deliver in the first place. Good training ensures that every single user interaction with that new system actually advances the strategic goals, rather than hindering them through errors or inefficient use. It links directly back to applying basic organizational models, KO2. You need to understand how people in the organization work and learn best to design effective training.
I've definitely seen training initiatives that just seemed to fall flat. Huge effort, lots of time, maybe even money spent, but users still seemed lost or resistant afterwards. What are the common pitfalls? Why does training sometimes fail so badly? And more importantly, how can we ensure our efforts are genuinely effective and lead to real adoption?
You're right. It's sadly common to see training investments yield very little if they're not designed and delivered correctly. Some common reasons for failure include, well, first, a simple lack of alignment with the overarching business goals. Training is done just for the sake of ticking a box, without a clear link to why it matters for the business. Then there's that inherent resistance to change we just talked about. If the training doesn't acknowledge and address those fears and concerns, it won't land well. Often there's a critical failure to account for the diverse needs, roles, and existing skill levels of the user base. A one-size-fits-all training approach rarely fits anyone particularly well. You have beginners and experts in the same room, maybe. Disaster. Poor measurement of training effectiveness is another big one. How do you know if it actually worked? If you don't measure, you can't improve. And finally, challenges in scaling training effectively, especially globally across different markets, languages, and cultures, can be a major pitfall. So, to counteract these, we really need to focus on embedding a few key best practices into our training strategy. First, strategic alignment.
Always clearly link your training objectives directly back to specific, measurable business outcomes. Why are we doing this training? What business results should it drive? Second, conduct a thorough needs assessment. This is absolutely not a one-size-fits-all situation. You need to look at it from multiple levels. Organizational, what are the overall business goals? Operational, what tasks need to be performed with the new system? And individual, what are the current skill levels and specific knowledge gaps of our users? Okay, this involves understanding what skills are actually required for a job using the new system, linking back to SO13, and then assessing where your people currently stand. What's the gap we need to close? Third, focus relentlessly on contextual and role-based training. Remember that statistic employees can forget up to 50% of new information within just an hour and maybe 70% within 24 hours. It's called the forgetting curve. So generic classroom training days often have very poor retention. Learning in the flow of work, right when the user needs it, is vastly more effective. Tailor the training content and delivery for different user roles, responsibilities, and even different geographical locations or languages. Embed knowledge directly into the learner's natural workflow as much as possible. Fourth, really, leverage in-app training technology. This is huge now. Integrate learning directly into the software application itself. This can take the form of interactive product tours for onboarding, step-by-step interactive walkthroughs for specific tasks, helpful tooltips that appear contextually, and easily accessible contextual help menus. Digital adoption platforms, or GAPs, like WhatFix, are excellent examples of tools that enable IT or training teams to create this kind of real-time contextual guidance without needing deep coding skills. A great case study is Sophos. They use something called Sophos Assistant, basically an in-app guidance overlay built with WhatFix for their complex firewall platform. It guided customers step-by-step through tricky configuration tasks right within the interface. The result? They significantly reduced support tickets and saved massive amounts of customer training time. That's the power of contextual learning. Fifth, utilize simulation and assessment tools where appropriate. These tools create safe, hands-on learning experiences by replicating the actual software application in a controlled, risk-free environment. Tools like WhatFix Mirror, for instance, allow for sandbox training where users can practice complex workflows. Some even offer AI role-play capabilities to simulate real-world interactions, like handling a customer support call using the new CRM. This lets students and employees practice applying systems, concepts, and workflows repeatedly until they're confident, without any fear of messing up live data in the production system. Sixth, develop a robust communication plan that clearly outlines the training objectives, the schedule, what's expected of users, and the overall roadmap for adoption. Keep people informed. Seventh, provide easily accessible moment of need support. When users get stuck while doing their job, they need instant help. This could be through AI-powered chatbots that can answer common questions, comprehensive self-help wikis or knowledge bases, or even embedded workflow assistance that provides guidance right when and where they need it. Eighth, make sure you establish clear feedback mechanisms and actively solicit feedback from users about the training and the system itself. Use surveys, polls, informal check-ins. Use that feedback to continuously iterate and enhance both your training programs and potentially the system configuration itself. Listen to your users. Ninth, implement continuous reinforcement. Learning isn't a one-time event. Offer regular reminders, quick tips, short refresher training sessions, or maybe micro-learning modules to combat that forgetting curve and ensure long-term retention of knowledge and skills. And finally, practice ongoing evaluation and adaptation. Regularly review the effectiveness of your training programs using actual performance data and user feedback. Be prepared to update and adapt your training content and methods based on lessons learned and the evolving needs of the users and the business. This kind of holistic, continuous approach ensures that training isn't just delivered, but that it's effective, drives adoption, improves performance, and ultimately maximizes the value of your significant technology investment.
That's a truly comprehensive and honestly much more effective way to think about getting users not just trained, but truly proficient and bought in. But even after you've achieved a successful launch, you've got well-trained users happily using the system. The journey is still far from over, isn't it? This brings us to what you called the long haul. System maintenance and evolution. Expert, what exactly is software maintenance? It sounds kind of boring, maybe. Why is this often overlooked phase so absolutely indispensable for the life of a system?
You've hit on a crucial point there, host. Software maintenance is, quite simply, any modification made to a software product after its initial delivery to the customer or deployment into production. It's a continuous process. It begins literally the moment the system goes live and extends throughout its entire operational life cycle, which could be years, even decades. And yeah, you're right, it's often considered less glamorous than shiny new development. Nobody really gets a big promotion or a flashy press release for fixing a subtle bug that nobody even noticed was there, right? But it is absolutely indispensable for the ongoing health, longevity, and effectiveness of any significant digital system. Think of it like owning a car. You don't just buy it, fill it with gas, and drive it into the ground until it dies, right? No. You get regular oil changes, you rotate the tires, you replace the brakes, you investigate those weird rattling noises when they pop up. Software is exactly the same. It needs ongoing care and attention. So why is this often unseen workhorse so critically important? Well, first and foremost, for security enhancement. Regular patches and updates are absolutely crucial for closing security vulnerabilities that hackers are constantly discovering and trying to exploit. Keeping sensitive data safe and maintaining customer trust is paramount. InvGate's blog, for instance, highlights this as a critical function of maintenance, and we've all seen the disastrous headlines when a company fails at this basic task. Second, it actually leads to significant cost savings in the long run. Proactive maintenance, fixing small issues, optimizing performance helps prevent much more expensive system failures, data corruption incidents, or large-scale emergency reworks down the line. Addressing minor issues before they become catastrophic saves money. Third, it ensures improved performance. Over time, systems can slow down, code can become inefficient, hardware changes. Maintenance involves optimizing code, adapting to new hardware or operating system versions, and fixing performance bottlenecks, all contributing to smoother, faster, more efficient operation for the users. And ultimately, good maintenance ensures the longevity of your systems. It keeps them running reliably, securely, and efficiently for their intended lifespan, maximizing the return on the initial investment. The hard reality is that very little software is ever delivered truly finished or completely bug-free. Most systems go live with some undiscovered latent bugs or areas that weren't fully fleshed out. Maintenance addresses these over time and, just as importantly, ensures the system remains useful and relevant in the face of constantly changing business requirements, user needs, and technological environments. For you, in BCIS 3389, this whole phase is about applying those basic systems concepts, KO3, in a very practical way, ensuring the ongoing functionality, reliability, security, and adaptability of operational systems. It connects your foundational knowledge directly to the long-term health and value of software in the real world.
Okay, so it's definitely not a set it and forget it situation. It's a continuous process of evolution and care. And it sounds like there are different types of evolution or maybe different reasons why we might need to perform maintenance. What are the main categories that this ongoing work falls into?
That's right. It's not all just bug fixing. The ISO AAC 14764 standard, which is a common reference point, categorizes software maintenance into 4 key types, each serving a very distinct purpose. The first one is probably what most people think of first: corrective maintenance. This is purely reactive. It involves identifying, isolating, and fixing defects, errors, or faults that emerge after the software has been released and are directly impacting its intended functionality. Think of a payment system bug that's causing certain transactions to fail intermittently, or a report that's generating incorrect numbers. You discover the issue, often through user reports, you diagnose the root cause, and you implement a fix to restore the system to its correct operational state. This type of maintenance is absolutely critical for keeping the software usable and reliable day to day. It's like getting an emergency repair done after your car gets a flat tire. Next up, we have adaptive maintenance. This type involves modifying the software specifically to accommodate changes in its environment. The software itself might be working fine, but the world around it changes.
These environmental changes could be things like needing to support a new version of an operating system, like Windows 11, needing to work with new hardware, integrating with updated external software components or APIs, or complying with new legal or regulatory requirements, like changes in tax laws or data privacy regulations. This is crucial for ensuring the software remains compatible and continues to operate smoothly within its evolving technological and business ecosystem. It's kind of like changing your car's tires from summer tires to winter tires, adapting to the changing external conditions. The third type is perfective maintenance. Now, this is more proactive and focuses on improving the software beyond just fixing problems or adapting to the environment. It involves enhancing functionality, improving performance, or increasing the maintainability of the software, often based on user feedback or evolving business needs. It's about making the system better than it was before, not just keeping it running.
Examples would include adding a new reporting feature that users have requested to make their jobs easier, optimizing a database query to make a slow screen run significantly faster, or improving the user interface to make it more intuitive. Perfective maintenance extends the software's usability, advances its value, and helps keep it relevant and competitive in the market. This is more like upgrading your car's engine for better fuel economy or adding a fancy new entertainment system improving its capabilities. And finally, there's preventative maintenance. This is perhaps the most forward-looking type. Its aim is to detect and fix potential issues or latent faults before they actually manifest as significant problems or failures. It's about foresight and risk reduction. This includes activities like performance optimization, restructuring code to improve clarity, refactoring, updating documentation, or cleaning up system state, sometimes referred to as software rejuvenation, like decluttering your computer's hard drive or cleaning out your fridge to get rid of old, unnecessary stuff and make everything run more smoothly and prevent future issues.
A key example is refactoring complex, convoluted code to make it easier to understand, modify, and test in the future, even if it's technically working correctly right now. This reduces future maintenance costs, technical debt, and improves the overall health and maintainability of the system. This is like taking your car in for its regular scheduled service checkup, changing the oil, checking the fluids to prevent major breakdowns down the road.
Those 4 pillars really define the ongoing commitment required to keep a system healthy and valuable over its lifetime. And what's really interesting is that the maintenance process itself for any of these types often mirrors the original development lifecycle, right? It can be thought of almost as a mini SDLC, a continuous cycle of activities. It usually starts with problem identification. An issue is detected, maybe through automated system alerts, maybe through bug reports filed by users, or perhaps just direct feedback during a review session. Then comes analysis. The maintenance team needs to understand the issue deeply. What's its impact? What's the root cause? How does it potentially affect other parts of the system or other interconnected systems? They're assessing the scope and figuring out what a potential fix might involve. The next step is design. Based on the analysis, they create a blueprint for the solution. This might involve designing new code, figuring out configuration changes, selecting an appropriate patch, or defining changes to data structures. Then you move to implementation. This is where the actual coding happens, or the configuration changes are made, or the patch is applied according to the design. Testing is, of course, absolutely critical here, arguably even more so than in new development sometimes. You need to ensure the fix works as expected and that it hasn't introduced any new problems elsewhere in the system. This is where regression testing becomes incredibly important, making sure you haven't broken something else while fixing the original issue. And finally, documentation. This step is so often overlooked or rushed in maintenance, but it's incredibly important for the future. Everything needs to be recorded meticulously. The nature of the original problem, the analysis performed, the design of the solution, the details of the implementation, and the results of the tests conducted. This creates a vital historical record for future reference, aids in knowledge transfer if team members change, and helps prevent repeating mistakes. And, good documentation ties directly back to the work done earlier in the SDLC. Those standard UML diagrams you learn to create in BCIS 3389, the use case diagrams, activity diagrams, class diagrams, KO4, SO13, they aren't just academic exercises. They form the foundation of strong system documentation. Clear diagrams significantly improve the maintainability of a system down the line. Speaking of maintainability, that's a key concept here. It's generally defined as the ease with which software can be understood, corrected, adapted, and enhanced. Software with good maintainability is cheaper and less risky to evolve over time. Poor maintainability leads to that accumulation of technical debt. Those quick and dirty fixes or poorly structured designs that save time initially but make future changes exponentially harder and more expensive. There are also significant workforce challenges often associated with maintenance, aren't there? It's sometimes seen as less rewarding or less prestigious work compared to building brand new things, which can make it harder to attract and retain skilled engineers. It sometimes gets outsourced or offshored, which can introduce communication challenges. And maintenance teams often require unique skills, sometimes needing to understand older, even outdated technologies or programming languages that new developers aren't familiar with. Effective communication, a key part of WO1, is absolutely crucial but can be hampered by time zones, cultural differences, and language barriers in globally distributed maintenance teams. It's a continuous, often underappreciated, but absolutely essential role in any technology organization.
And this brings us nicely to the idea of modernizing maintenance itself, host, moving beyond some of the inherent challenges we see, especially with older legacy systems. The problem with true legacy systems can be really significant. They're often written in languages that are now obsolete or have very few developers skilled in them. They frequently lack adequate documentation because it was never created or wasn't kept up to date over years of changes. Their internal structure might have deteriorated badly due to decades of patches and quick fixes, making them brittle and hard to understand. And often the knowledge about how they work resides in the heads of just a few long-serving experts who might be nearing retirement. All this makes maintaining these systems incredibly difficult, risky, and expensive. Sometimes it becomes practically or economically unfeasible, leading to that massive accumulation of technical debt we talked about. Trying to fix a critical bug in a 30-year-old mainframe system with virtually no documentation written in COBOL, where only one person left in the company kind of understands it. Well, it's like trying to perform brain surgery in the dark with only a fuzzy photograph as a guide. It's tough. However, the landscape for managing maintenance activities themselves is evolving dramatically, largely thanks to modern web-based maintenance management software, often called CMMS, or sometimes EAM, Enterprise Asset Management Systems. These modern solutions offer huge advantages over older, often on-premise or even paper-based legacy approaches. First, they provide significantly enhanced functionality. They move way beyond just tracking basic work orders. They offer sophisticated features for planning and scheduling preventive maintenance, detailed asset tracking, often using barcodes or QR codes, real-time reporting dashboards, and powerful data analytics capabilities. This empowers maintenance teams to become much more proactive, efficient, and data-driven in their decision-making. They also generally lead to a much lower total cost of ownership, TCO, compared to traditional systems. Unlike legacy software that often required huge upfront investments in licenses, servers, and databases, plus ongoing hardware maintenance costs, modern web-based CMS solutions are typically delivered via a software-as-a-service SaaS model. This means a predictable subscription-based pricing, usually per user per month. It drastically reduces the upfront investment, eliminates the need for the company to manage the underlying hardware and software infrastructure, and helps avoid that technical debt, often associated with older monolithic architectures. Plus, they're often designed to be much more intuitive and user-friendly, reducing training time. Furthermore, modern CMMS systems offer seamless integration and scalability. They're usually built with application programming interfaces, APIs, that allow them to integrate relatively easily with other critical business systems, like your ERP, Enterprise Resource Planning System for finance and inventory, or your CRM, Customer Relationship Management System for customer data. This breaks down data silos, improves data accuracy, and enhances collaboration across departments. They also scale effortlessly. Need to add 10 more users or activate a new module. It's typically just a configuration change or a subscription adjustment without requiring major infrastructure overhauls or impacting existing data. This flexibility is a massive improvement over the rigid architectures of many older systems. You also get vastly superior real-time tracking and reporting. Gone are the days of technicians filling out paper forms or manually entering data into clunky desktop applications at the end of their shift. Modern CMMS often use mobile apps, allowing technicians to receive work orders, record their progress, log parts used, and capture data, like photos or meter readings, directly in the field in real time. Features like QR code scanning make identifying assets instant and accurate, and the built-in analytics tools can generate insightful reports and dashboards instantly, showing things like maintenance backlogs, asset downtime trends, cost per asset, and technician productivity. These insights help managers identify recurring problems, spot inefficiencies, and continuously optimize their maintenance strategies. Overall, web-based CMMS just offers much greater cost effectiveness for most organizations. By leveraging cloud-based solutions where the software vendor hosts and maintains the application and infrastructure, companies significantly reduce their own hardware, software, and IT support costs.
And interestingly, in terms of the process or models used for managing maintenance work itself, we see an evolution that mirrors software development methodologies. The traditional waterfall model, linear, sequential steps, can still be used for very simple, predictable maintenance tasks, but it's often too rigid for dynamic environments. An iterative model, breaking maintenance work into smaller cycles or releases, allows for more flexibility, continuous improvements, and periodic updates based on feedback or changing priorities.
But increasingly, especially for more complex systems or ongoing enhancement work, perfective maintenance, the Agile model is proving highly effective. Using short sprints, maybe 1 to 4 weeks, maintenance teams can quickly prioritize incoming requests, bugs, enhancements, adaptations, collaborate closely with stakeholders, deliver working fixes or improvements rapidly, and continuously adapt to changing needs. This ties directly back to your KO5 on applying project management methodologies. Understanding when Agile principles can bring significant benefits to the ongoing maintenance lifecycle is a key skill. To continuously improve maintenance effectiveness, regardless of the model used, some key tips always apply. Look for opportunities to automate routine tasks like running regression tests or monitoring system health. Develop clear processes to prioritize issues effectively, focusing resources on the most critical items first. Make a real commitment to regularly updating documentation. W01. It's not glamorous, but accurate documentation saves enormous amounts of troubleshooting time later. And continuously train your team, ensuring they have the skills needed to maintain existing systems and adapt to new technologies or tools being introduced.
That's a really powerful look at how we can modernize the ongoing care and feeding of our systems. But even with the best planning, the best tools, the best processes, the road to digital success from initial implementation right through years of maintenance is often a real gauntlet of challenges, isn't it? Expert, thinking back maybe to some of the more spectacular system failures or troubled projects you've witnessed or heard about, what was the common thread? What ties into these common roadblocks that seem to derail even the best laid implementation and maintenance plans, KO5?
Oh, absolutely. There have been some infamous ones, and you're right, there are definitely recurring themes, common failure points that pop up again and again. If we draw lessons specifically from large-scale ERP implementations, which are notoriously complex beasts, we see these issues magnified, but they apply broadly. Even with supposedly simpler SaaS and cloud solutions today, which definitely ease some burdens, the core challenges often remain. And frequently, they boil down to the human elements. Simple human error, critical knowledge gaps, communication breakdowns, unrealistic expectations, and sometimes just plain old burnout on long, difficult projects. But these often stem from broader, more systemic roadblocks. So what are these key roadblocks we keep seeing? First, and we've hit this hard already, change management, or rather the lack of effective change management. Users naturally resist switching from systems they know, even if the old system is terrible. If you don't proactively manage that human transition, address the fears, communicate the why, and provide support, your technical success is irrelevant. The project will likely fail the adoption test. Then, goal misalignment. This is huge. If there's no clear consensus among stakeholders, business leaders, IT, and users about what the new system should actually achieve, what success looks like, you're building without a clear target. Different teams might pull in different directions, leading to a system that tries to be everything to everyone and ultimately satisfies no one well. Often, there's a fundamental misunderstanding of the technology itself. This can cut both ways. Sometimes organizations underestimate the functionality needed, leading to a system that can't support critical processes. Other times, they get seduced by fancy features and overinvest in unnecessary complexity that users don't need, and that makes the system harder to implement and maintain. People simply don't grasp the scope or the implications. A really critical one is the lack of dedicated resources, particularly failing to dedicate a strong, cross-functional implementation team to own and drive the project. You absolutely cannot expect a complex system implementation to succeed if people are only working on it part-time, squeezed in around their real jobs. It needs dedicated focus and authority. Poor planning is almost always a factor in failures. Failing to adequately define the project scope, establish realistic timelines, identify risks upfront, and plan resources. It's just a recipe for disaster. This invariably leads to chaos down the line, and that often leads directly to scope creep. This is a classic project killer. Uncontrolled changes and additions to the project requirements that sneak in after the initial plan is set. Each small addition seems reasonable on its own, but collectively they expand the project beyond its original boundaries, blowing the budget and the schedule. It's death by 1,000 seemingly minor requests. Data migration issues are so frequently underestimated. The sheer complexity of extracting, cleaning, transforming, and loading vast amounts of critical, often messy or incomplete, data from legacy systems into a new system can cause massive delays, data corruption, and user frustration if not planned meticulously from the very start. Garbage in, garbage out. An inadequate budget is another common pitfall. Companies often underestimate the full cost of implementation. They might focus only on the software license fees, forgetting about essential costs like hardware upgrades, network improvements, extensive user training, customization work, integration development, consulting fees, and crucial ongoing support and maintenance costs. You have to budget for the total picture. Broken integrations or bad customizations can cripple a new system. If the connections to other essential business applications are poorly designed or implemented, or if the core software is overly customized in complex, non-standard ways, it can lead to system instability, make future upgrades incredibly difficult or impossible, and create a fragile Frankenstein's monster of software that's a nightmare to maintain. Communication silos are deadly. A lack of clear, consistent, and open dialogue among all stakeholders, the project team, business departments, IT, vendors, end users, management, can completely fragment efforts. It leads to misunderstandings, misaligned expectations, duplicated work, and critical issues falling through the cracks. Having no response plan for unexpected problems leaves a project incredibly vulnerable. When things inevitably go wrong during implementation or post-launch, and trust me, they will go wrong, you need a predefined playbook for how to respond quickly and effectively to minimize downtime and disruption. Hoping for the best isn't a strategy. We've talked about lack of training, but it bears repeating. If end users aren't adequately educated and supported to fully utilize the new system's capabilities, adoption will be low, frustration will be high, workarounds will proliferate, and ultimately the system simply won't deliver the promised value or ROI. And finally, a really common mistake is having no post-implementation support strategy. Too many organizations assume the project is done the moment the system goes live, but go live is just the beginning. Ongoing support, monitoring, bug fixing, and continuous improvement are absolutely vital for long-term success and ensuring the system continues to meet business needs.
Wow, okay, that is a truly daunting list of potential landmines waiting to blow up a project. But these aren't completely insurmountable obstacles, right? There are ways to navigate this minefield. For our listeners, the students who will soon be facing these challenges in the real world, what's in their toolkit? What are the key mitigation strategies and solutions they can employ to navigate these challenges and dramatically increase their chances of success?
Absolutely not insurmountable. Difficult, yes, but definitely manageable with the right approach, vigilance, and the right strategies in place. First and foremost, comprehensive planning, tying back to KO5, is utterly non-negotiable. Before you write a single line of code or configure anything, you must clearly define the project scope, set realistic goals, and identify the necessary resources: people, budget, time. Assemble a dedicated, empowered, cross-functional team critically. This must include not just IT folks, but key representatives from the business units who will actually use the system and understand the processes. Conduct thorough data preparation and migration planning early in the process. Don't leave it as an afterthought. Perform rigorous risk assessment to identify potential problems like the ones we just listed, and develop solid mitigation strategies for the most critical risks. And crucially, establish clear communication plans and regular feedback loops from the very beginning, ensuring everyone stays informed and aligned. Second, to effectively manage change, KO2, you have to be proactive and empathetic. Open up multiple lines of communication early and often. Involve all key stakeholders right from the start to build understanding and foster a sense of ownership. It's their system too, not just IT's. Actively demonstrate the value of the new system. Don't just tell them it's better, show them how it will make their jobs easier, or help the company succeed, focusing on the what's in it for me, WIIFM. Provide that ongoing, tailored training and readily accessible support we discussed earlier. And when resistance inevitably arises, be prepared to address it constructively, using persuasion, highlighting benefits, maybe offering incentives, leveraging strong leadership support, and addressing concerns genuinely, not dismissively. Third, ensuring quality requires relentless diligence throughout the entire process. Thoroughly test everything, especially all integrations with other systems and any customizations made to the core software. These are common failure points. Implement continuous monitoring systems and feedback mechanisms after go live to catch performance issues or emerging bugs quickly. Track key quality metrics like defect density or code test coverage. Maintain comprehensive, up-to-date system and user documentation, WO1, because accurate records are absolutely invaluable for troubleshooting, training new users, and planning future enhancements. And establish clear configuration management processes to strictly control any changes made to the system after go live, preventing unauthorized or untested modifications that could break things. At a broader organizational level, certain cultural tactics can foster an environment that's much more conducive to successful change and implementation. Companies should strive to welcome opportunities for change, viewing them as chances to improve and innovate rather than threats to be feared or avoided. They need to create an environment that doesn't punish honest mistakes, especially during the learning curve of a new system. This encourages experimentation and faster adoption. Leaders need to clearly define growth plans associated with the change, showing employees how the new system fits into the bigger picture. It's important to set realistic criteria and expectations for new opportunities and systems, avoiding overpromising. And critically, the organization needs to maintain a focus on long-term benefits over potentially disruptive, short-term financial metrics or hurdles. True digital transformation is a marathon, not a sprint. It requires sustained commitment. Ultimately, avoiding outright failure and achieving sustainable success boils down to executing several core actions consistently well. Create a clearly defined, well-organized, and realistic plan. Communicate that plan effectively, consistently, and transparently to every group involved. Define clear, measurable goals, KO1, so you can objectively track progress and understand what success actually looks like. Build a solid management structure, KO5, with clear roles, responsibilities, and authority to provide effective oversight and make timely decisions. And proactively identify and properly manage risks throughout the entire life cycle, from initial concept right through to ongoing maintenance and eventual retirement. It's this kind of holistic, disciplined approach that ensures not just a successful launch day, but sustained value and continuous evolution of your critical digital systems over the long haul. Hashtag outro.
Wow. We have really covered a lot of ground today. We've journeyed through that entire life cycle, haven't we? From a carefully designed system concept through the complexities of implementation, choosing the right strategy, navigating the minefield of testing, all the way to the crucial ongoing commitment of maintenance and evolution. We've seen how implementation is so much more than just a technical task. It's this intricate dance of strategic choices like those deployment strategies. It involves incredibly rigorous testing at multiple layers to ensure quality. And perhaps most importantly, it's about skillfully managing that human element through thoughtful change management and really comprehensive user-centric training. And then we highlighted how system maintenance isn't just an afterthought, but the ongoing commitment that truly ensures a system's longevity, its security, and its sustained performance over time. It's constantly adapting to new environments, evolving user needs with its own cyclical processes and increasingly sophisticated modern approaches. It really is a continuous pursuit of operational excellence in the digital world.
Absolutely. And for you, our listener, especially if you're in BCIS 3389 or a similar program, please recognize that these aren't just abstract academic concepts we've been discussing. These are the real-world practical skills, things like applying economic and organizational models, KO1, KO2, to understand impact, leveraging structured project management methodologies, KO5, to guide execution, crafting clear and effective communications, both written and verbal, WO1, and designing robust, maintainable systems using tools like standard UML diagrams, KO4, SO13. These are the very skills that will truly distinguish you in your future career. You're essentially learning how to be the architect, the strategist, the diplomat, and the problem solver all rolled into one, the business. The person who ensures that technology genuinely serves the needs of the business, turning abstract ideas and complex requirements into tangible, value-driven solutions that actually work in the real world.
Well said. If this deep dive has sparked your curiosity, maybe given you that aha moment about how systems truly come to life and stay alive, please do hit that like button down below. Subscribe to our channel for more insights like this. And maybe share it with a classmate or a colleague who you think needs to hear it. And don't forget, all those supplementary resources, links to things we mentioned, maybe some further reading, they're all waiting for you down in the description below.
And just as a final thought to leave you with, as you go about your day-to-day, maybe interacting with dozens of different systems without even thinking about it, consider this. What's one system you rely on daily that just works flawlessly, almost invisibly? Maybe your banking app or the traffic light system or the streaming service you use. And then pause for a second and wonder what might be happening behind the scenes. What complex processes of implementation, ongoing maintenance, adaptation, and correction are constantly at work to make that seamless experience possible for you.
Behind every single tap, every swipe, every click, there's a system that someone, maybe someone like you in the future, designed, implemented, and continues to nurture. Until next time, keep learning, keep questioning, and keep building the future one process at a time.